All right, let's jump right into this explainer. Today, we're putting on our statistical detective hats to demystify the actual mathematics behind proving when a test question is, well, just plain flawed. We're going to look directly at the real data science that test creators use to validate exams and separate genuine assessment from random, frustrating noise. Section 1. The bad question problem. Identifying flawed items. Look, we have all experienced that universal frustration of a completely tricky test question that somehow just penalizes the most studious learners. Think about those times you literally knew the material inside and out, but the wording of one specific question was so bizarre you got it wrong. Meanwhile, someone who just guessed blindly managed to get it right. But how do you mathematically prove a test question is unfair? From an evaluator's perspective, relying on a gut feeling or student complaints just isn't enough. We need a hard, systematic way to identify when a question fails. And the answer to that challenge lies in building a mathematical bridge between a student's performance on one microscopic item and their macro-level results on the entire exam. Moving on to Section 2. Meet the R-Biserial, Advanced Item Analysis. So, enter our statistical hero for advanced item analysis, the R-Biserial. Technically, this is a calculation that measures the strength and direction of the relationship between students' overall test scores and their performance on a specific item. But simply put, this metric tells us if the exact same students who are doing well on the whole test are the ones getting this specific question correct. It is fundamentally just a check for consistency. If an exam is well designed, a student who scores a 95% overall should theoretically have a much higher probability of getting, say, question number 4 right compared to a student who scores a 40% overall. Section 3. Anatomy of the equation. Deconstructing the math. Okay, here is the full calculation. Now take a breath. Please don't let the Greek letters and square roots intimidate you. We can actually take this complex algebraic formula and deconstruct it into really intuitive, bite-sized pieces. We're going to treat this equation like a biological specimen and just zoom in on its anatomy, variable by variable. At its core, it's essentially just a fraction multiplied by a square root. It relies on a few key data points: the average scores of different groups, the overall spread of scores, the proportion of right answers, and the total headcount of test takers. Let's start with the top part of that fraction. The core of the formula's numerator is literally just a statistical tug-of-war. It directly compares the overall average scores of the students who got the item right against those who got it wrong. We have M correct. This is simply the average total test score of the students who answered the specific item correctly. We pit that right against M incorrect, the average total test score of the students who answered incorrectly. By subtracting the wrong group's average from the right group's average, we immediately see who this question favors. If the question is actually doing its job, the group that answered correctly should boast a significantly higher overall test average than the group who got it wrong. Make sense? To finish building out the equation, we bring in a supporting cast of variables. We simply take that tug-of-war difference we just talked about and divide it by sigma total. That represents the standard deviation, or basically the overall spread of the total test scores. This step standardizes our number. Finally, we multiply by a factor tucked under a square root that accounts for p, the proportion of students who answered the item correctly, and n, the total number of students. This back half of the equation essentially scales our result. It gives it the appropriate weight based on how large the class is and how difficult the question was overall. Section 4. Decoding the scale. Interpreting the values. Now, calculating the number is only half the journey, right? Interpreting it is where the true value lies. If your resulting calculation is closer to +1, you have a strong positive correlation. This is great news. It means students who scored high overall tended to answer the specific item correctly. The question is accurately separating those who know the material from those who don't. But values closer to 0 mean absolutely no correlation. It's just a coin toss. There's no clear relationship between the overall score and this item. Finally, negative values mean an inverse relationship. And guys, this is your massive red flag. This happens when students who scored low overall actually answered the item correctly more often than your high-scoring students. When you see a negative number, it usually points to a trick question, maybe a typo in the answer key, or just overly confusing wording where the top students totally overthought the problem while the blind guessers somehow succeeded. And finally, Section 5. Upgrading your analysis. Improving test design. So how do you actually leverage these insights to improve your real-world test designs? I mean, we don't just calculate complex statistics for the fun of it. We use them to build fairer, more accurate systems. By utilizing the R-Biserial when you have access to individual student scores, you empower yourself with advanced item analysis. You can literally catch flawed test questions before they ruin your data. It provides much deeper, actionable insights into test quality than just looking at a basic class average. Instead of guessing if an exam was fair, educators and analysts can empirically prove which questions are pulling their weight, which ones are harmless statistical noise, and which ones are actively penalizing the best students. As we wrap up this explainer, I want to challenge you to evaluate your own assessments differently. Are they truly measuring knowledge, or are they just creating statistical noise? The real beauty of the point-Biserial correlation coefficient is that it completely removes human bias and emotion from the grading process. It serves as this ultimate objective lie detector for test items. But it leaves us with a pretty fascinating question to think about. If a simple mathematical formula can expose the hidden flaws in how we test knowledge, what other blind spots are hiding inside the ways we measure human potential?